Yep.
And that's good. Why? How would you use
Well,
that?
that's good because now if you know the short circuit for every single class, right? So now we know exactly which weights belong to each class. We can compare. So all the weights that are common, we can ignore because they're actually just noise. And so now we know the exact weights that are specific to just one class.
Welcome to season 2 of Practical AI, everybody. My name's Jeff. I'm with Peter Lynn. We are sponsored by Pocket AI. Pocket AI is a tool used to perform surgery on your models. This surgery is something that will make your models way better. While everyone today is talking about RAG and refinement, Pocket AI allows you to edit the weights of your model directly, something that no one's really doing today. Peter, we are in a series called Training Your Own Model, and you are giving us a little bit of a demo on using Pocket AI and the edit method to do this surgery that we've talked about a little bit. And our last episode, our last conversation, you had shown us some of the lists, some of the graphs of data itself, and how you're able to kind of um, weed out which epochs, individual records or individual classes did well on, which ones they failed on. And then you got into a little bit about how you use those to improve your data sets, but also improve the model itself. And then you got into the weights where you're like actually looking at the weights themselves. Tell us a little bit more about this, extend this conversation and where you can go from here.
Yeah. So before we jump into that, this is term in AI and machine learning where basically all the weights in the model, we call it opaque, meaning that you can't see into it, right? So it's a black box. And so this is a topic of research for the AI safety people, AI alignment people, where they want to be able to identify what weights do what thing, right? So it could be a language model, it could be an audio model from voice to text, it could be a computer vision model. But because today all the weights are opaque, you can't see into the model, you can't identify which weights do what. And so that causes a problem where you don't even know where to start. And so this is kind of the problem that I've been working on for 10 years, which is like, well, there ought to be a way for me to figure out what those weights are doing. And so the key really is to look at changes in the weights over time, right? So if I go to Pocket AI, so when we go to the report, as I mentioned last time, the first thing we do is we look at each class. We look to see kind of patterns of good performance versus bad performance. And the reason why that's important is this allows us to then compare the weights directly. And once you can do that, you can start to isolate exactly which weights contribute to a particular model. So for example, the purple diamond one is cat. And we see that cat did well on 13 and on 18, but it was bad on 14 and 15. And if we look at the other classes, we can see, wait a minute, there are classes that actually improved between those two, 14 and 15. So that means that when the model was training, it adjusted weights such that it made it worse for cats, but it made it better for horses, and it made it better for, what's the, let's see, it's a blue circle for airplanes. So whatever weights it adjusted for those two classes caused these other classes to get worse. And so that tells us that there's weights that are common to these three classes that are causing this effect. And by comparing the weights between 14 and 15 and 18 and 13, we can then identify exactly which weights are causing these two to improve and this one to get worse.
Now, this is essentially correctness or accuracy, right? And so last time you basically demonstrated how normally your accuracy graphs is just one line. And yeah, there you go. And it's just that's just basically that's all the classes, right? That's all
Yep.
of them as one line. And what you've done here is you've opened that up to show all the classes that you have available that you're training on. And so now the first step is to just organize by class, right? So you can kind of get a feel for the accuracy line that we saw more generally has a lot going on specifically.
Right. So the thing that people have struggled with is that when you look at one line, you're missing the detail. So it's kind of, if you go back to the saying, the forest for the trees, right? So here we see the forest, but we don't know what's causing the forest to die. Like, why is a forest not healthy? From this line, you can't tell. The only way to know is if you actually go into the forest and you do a survey and you go, okay, why are pine trees doing well and why are oak trees doing bad? Right. So this is kind of that approach of like, let's dive into the details and let's look for patterns that we can exploit. And it turns out that if we take epochs that were basically the same, so like for example, here we have the blue triangle, which is horse. It did well on 32, 34, and 36. So if we average those ones, we can kind of get the average weight that produces that level of accuracy for horses.
And so in
And
that instance, you just whatever the math is for essentially each of the weights on that, you've just said add these three together and give me the average and apply that metric, that number
yep.
to the weights, and that's essentially the average. Is there a reason why it's average and not a third or whatever? Is there a reason?
So the reason is, so as you're training over thousands or millions or billions of pieces of data, the error correction is going to make these little adjustments trillions of times. Sometimes it's good, sometimes it's bad. But if we average it over several epochs, this allows us to basically reduce the noise,
Okay.
right? Because now we're saying, okay, we see the epochs that had basically the same performance. If we average those, we can filter out any noises and isolate the important weights. And then when we take epochs that were bad, so in this case, like 35 and 37, we can average those two. And it turns out that when you do that, you can actually identify the exact weights for one class. And you can then apply that to any epoch and it'll always turn out the same result. So that's a way
But
of short the model.
okay, you just use the word short circuit, and we're going to get to that. But before that, there's an important step there. So I'm just going to try to dumb this down so I can understand it. So you have at least two instances of good and at least two instances of not so good, right?
Okay.
You add those together to get an average. And then the step in there is you're using those. So when you run it again with the averages, you've got an average high and an average low,
Yep.
right? But then what you've done is you've created a view of the differential between those two, right?
Yep.
Can you show that really quick before we get into the short circuiting?
Yeah. So here, let's see, actually on this computer, I don't have one, but so basically, once we've done that, we can identify the difference between the good average and the bad average, and that tells us exactly the exact set of weights at every layer that is contributing to that, right? And so it shows up some of this where the darker weights are the ones that are the most important. And what happens is when you do that comparison, it's really a tiny subset. It's less than like 10%.
And this is each layer of
Yep.
the model has
Yes.
these these changes. Black is more change, white is less or no change. And so first thing you could do is just take out all the white because it's irrelevant. It's
Yep.
not doing anything for this thing. And then would you focus on clusters and patterns, or would you focus on the ones that have the most change, or
So
both?
the nice thing is once you found the short circuit for one class, you can find the short circuit for all the other classes. And so
Okay,
now
so
we gain
explain short circuit real quick again, because
a
I
short
kind of
circuit. Think of it this way. Um, let's say you're in a race, and the race is 10 miles, and it takes this kind of a spaghetti route across the city, but there's a street that you can take that just takes you from the start to the end, and you can skip 9 miles, right? So this it's a short circuit that allows you to get from point A to point B much faster. That's always gonna get you there in a predictable way, right? So if you think about the weights of a model, it's like this noodly route where data coming in can take any number of routes to get to the end. And every time you feed it data, it's going to take multiple routes in different ways to get to the end. So circuit just says, okay, when you get this data, you're going to take the same path every single time.
Okay. And it doesn't matter what data it gets on the short circuit, it's always going to produce the same output, right?
Right, right. So that's why it's a short circuit, because no matter what you give it, it'll give you the same result.
So in this case, you give it ship, you give it horse, you give it cat, and everything comes out cat.
Exactly. Yep.
And that's good. Why? How would you use
Well,
that?
that's good, because now if you know the short circuit for every single class, right? So now we know exactly which weights belong to each class. We can compare. So all the weights that are common, we can ignore because they're actually just noise. And so now we know the exact weights that are specific to just one class. And so now all you really care about is just the weights for that one class. And if you know that, then you can predict with high accuracy what the class is.
And so if I think about this just from a application perspective, if I'm doing diagnostics and I really want to know if this particular assay on this slide is going to result in a diagnosis for stage 3 breast cancer.
Right.
This would allow you to prove essentially that if, yeah, we've trained the model, we know that these weights return breast cancer.
Yep.
If you get these weights light up, if you get breast cancer or whatever result, it's basically guaranteed that this is breast cancer. Is
Right.
that
Yes. So that
okay?
means that basically, once you know the exact weights that are specific to just that one class, you have a proof. So whether it's for computer image, whether it's for some other kind of model, some kind of data, you have basically a proof that given a certain input, it will get this output.
Pretty cool, Peter. So where do you go from here with this?
So again, so this is a tool. So then when people train, they don't have to sit there and wonder like, oh, do I collect another 4 million pieces of data and then spend 6 months training and then wonder, well, is they going to get it right? You can go in and you can actually figure out like, okay, this is what's happening.
Well, what I find interesting is that right now people collect data, train their model, and that's training. What you're doing is you're collecting data, you're training, and then you're adjusting the data set based on the results of the training and the test, right? So now you're doing some just basic data sort of management.
Yep.
But then you're doing the sort of differentials look at the weights, and you're pruning, you're averaging, you're essentially editing the weights. So you're adding sort of process steps on the training, which nobody's doing right now.
Yeah, mainly because no one has bothered to explore this for a couple of reasons. One, originally, when neural networks were first created, this is before Jeff Hinton, computers were really, they weren't really powerful, right? I mean, they were a lot less powerful than your smartphone, right? They had a lot less memory. I mean, today we take for granted that you have gigabytes of memory. Back then, it was kilobytes was a luxury. And so no one could do this because the processing power just wasn't there. You couldn't do it. And as things have grown, people have not gone back and thought about like, well, okay, could we actually do this? Everyone's been kind of stuck in this mode of like, well, this is how it's been done for 30 years, and so we're going to keep doing the same thing.
Got it. Well, glad that someone's gone back in time to get us closer to the future here. So, Peter, wonderful stuff. Thanks for doing this. We will probably will wrap up our training your own model series, unless we come up with another idea later. But as always, ask us questions. You can make comments in the YouTube thing that we send out. And if you have topics you'd like us to cover, we'd love to hear about those as well. Peter, thanks again, and take care, everybody.